Hello, my name is John Cleland. I'm a retired electrical engineer. I worked for 37 and a half years in the transmission planning department of TVA, the Tennessee Valley Authority. During those 37 and a half years, I worked in pretty much every aspect of the engineering that went on in that department. But as my career progressed, one thing I became very interested in was the database and the creation of load flow, fault analysis, and dynamic stability base cases from the database. The original database was written in early 1980s in Fortran on a Prime mini computer, needed to be replaced. So I began looking at things. I ended up writing a new database using Visual FoxPro that mimicked the old program. Then over the years, that program was enhanced and expanded in many times, but it is still the program that TVA uses today. After I retired, I wrote two programs. One is a transmission line constants program. There's a YouTube video out on the net. If you'd like to look at that, you can see it calculates transmission line impedances. The second thing I looked at was writing a database similar to TVA's Visual FoxPro database, and I used Visual Basic and SQL Server. Now that's a very big undertaking, so actually all I've done is a small portion of it, but I'd like to show that to you. Not that it is exactly what someone would want, but it does illustrate some of the things you can do, some of the things similar to what TVA did. And I guess I don't really know exactly what I'm shooting for here. I guess I'm looking for a partner or someone to sponsor me, or just someone who needs maybe a little help getting started on something similar to that. So I'd like to show you a demonstration of what I've done so far, and there'll be several points to discuss. At any rate, while I do that, I want to make sure you understand that I am no longer a TVA employee, and any representations I give of what they do or did or whatever is just my memory, and I am not representing TVA in any way. So let's go ahead and get started showing you what I've done so far and see if it's something you would be interested in. Thank you. Before I begin, I want to show you the sample system that I'm going to be using as the example for this database. This is totally fictitious, just totally made up. It consists of a Baltimore 500 to 161 kV substation, one 500 line to New York, and four 161 kV lines, Pittsburgh, New York, and two to Washington. And initially, I'm going to show that the Baltimore, Washington #1 line is direct to Washington. And then later on, I'll show you how to add a line, add a bus and add a line. And then also I'm going to add the Pittsburgh 500 line, this one at June of 2014 and this one at January of 2017. Now let me, the program I've already got open. Let me start out with buses, edit buses. First you're presented with a list of all the buses in a browse mode. And if you, for example, normally you would expect this list of buses to be extremely long, and let's say you want to find a particular bus, say it includes the word York. I can filter, and I actually give you the filter expression that you can edit yourself and create different filters. If you want to remove the filter, you can go back to the full. But let's go to the Baltimore 500 kV bus. This is the bus data. Now, this will be a fairly high level flyover of the database and how it looks, but let me show you a few hallmarks of the database. One is that it is a date-based, in and out of service date-based database. Now, I've seen PTI's model on demand demonstrated, and from what I gathered, it is a parent-child database. You start with a parent case, and all your database entries are modifications to the parent. This is an absolute database, absolute date database. So you keep everything. You can go back and look at things in the past. You can create cases well in the future just based on whatever changes you make. Another hallmark of this database is that anytime you make a change on the screen, let's change this to 30 degrees. Anytime you make a change on the screen, the background of the cell that you're working in is going to change to a different color to illustrate to you that that cell has changed. Now, it doesn't make a lot of difference in this fairly simple. Let me change this for example, just for fun. It doesn't make a lot of difference in the buses form because there's not a lot of data there, but in a little bit when we get to line ratings, you'll see how very valuable this feature is. Another feature we have is this checkbox here, load flow bus. In many cases, there are buses that you may not want in your load flow, but still you need them in the database because they're needed in a fault analysis case. For example, if you have a 161 to 69 kV transformer feeding radial 69 kV load, but you have decided in your load flow to represent all of that radial load at the 161 kV bus, you wouldn't want to model the entire 161 to 69 bank and all those 69 lines in your load flow. However, when you're making a fault analysis case, if that 161 to 69 kV transformer is a YY delta transformer and has a zero sequence current originating from it during a 161 kV fault, you would want that transformer. So you can label the high side bus as a load flow bus, and you can unlabel the low side buses, low side and the tertiary bus, as non-load flow buses, so that when you make the case, you'll see if it's a load flow case, you'll only get the high side bus. If it's a fault analysis case, you'll get all three buses. Now, every type of data has a uniqueness specification. In the case of bus numbers, it is the bus number itself. There is only one bus in this database and can only be one bus in this database, numbered 532700. Another hallmark of this database is data validation. Now, I don't have a lot of data validation in here, but for example, if I change this to a 230 kV bus, I'm going to get a little note because I have told the program that an 8 code at the start of a name is for 500 kV, and it won't let me put a 230 kV bus, or at least it asks me before I do, and I can say no, and it'll go back to what it was. So there's data validation. That's another hallmark of this database. Now let's move on to lines. You can see here's the 500 line, Baltimore, New York 500, and the 4 161 kV lines. So let's pick one of these lines. Now, again, there is the ability to generate a filter. Let's use York again as the filter basis, and you can see the filter expression and then the results of the filter. And you can filter on 2 names, which will give you every line that has one of those names at one end and one of those names at the other end. At any rate, let's go back. Okay, I'm going to look at the Baltimore, New York 500 line. And as far as the uniqueness of the line records, the way I've designed the database, there is only one Baltimore, New York 500 line, 532700 to bus 533100, circuit 1. There can only be one line with that specification. Now, the TVA database extends that to the in-service date, in and out of service date, so that you can have multiple instances of a line as long as their in and out of service dates don't conflict with one another. I also give you the ability to assign a line to a diagram, so that when you're drawing plot diagrams, impedance diagrams, you would be able to assign that to a diagram, and you can actually use the diagrams to assist you in making sure the database is correct. If the diagram looks right, you draw the diagram, and if it matches the database, then you've got a little more confidence that the database is correct, in service date, etc. There are many times when you build a new station in the middle of the line, the line name for a given node-to-node section of that line may change. So I've given the ability to have it belong to more than one transmission line by name. And then finally, I've allowed you to identify common corridors. This is to assist you in the new compliance regulations that require studies of contingency studies for corridors in which more than one line occupy the same right-of-way for more than a mile. Then there is the impedance record. This is a child record of the line record, and it has an in and out of service date. Now there can be multiple instances of the child record based on in-service dates. So you could have an impedance for 3 years and then a different impedance beyond that based on the fact that maybe the line has been reconductored. But you got length, impedance, zero sequence impedance, and at some point I would add the ability to say what conductors are involved in this line and do a validation between the conductors in the distance and the impedance. Try to guarantee that you don't put an impedance in that doesn't seem to match distance and conductor. Another thing I've got is a history. There is a history of all the changes to all these records. Now, what I've done is the history, when you put a new record in, the history only enters one instance of that line change because it's a brand new record. Now, any further changes to that line record will cause every single field change to be recorded in the history log. Let me look at the ratings. Now this is a very, very involved screen here, and some people complain that I'm bad about making my screens too busy, but when you think about it, you've got a lot of information available to you on this line. Now again, like the impedance record, this rating record is a child of the line record, so there can be multiple instances of this. Let's suppose you have a change in, again, in conductor, for example, and it needs to calculate a different rating. You can have a different record with a different time period using different conductors, and the rating records, there'll be two rating records at that point as children of the main line record. Now one of the hallmarks of this, now let me show you again, talking about the changes and how they show up. If I make this a 4,000 amp trap, you can see that I now, and let me make this one a 4,000 amp trap too, so that you can see how the rating changes. I increase the rating of both traps at both ends of the line, and now my planning ratings have changed for the 30C, 20C, 10C, and 0 degree C ambient temperatures. If I put a larger conductor, let's put 1351. Again, you'll see that I forget where it was, maybe right there, the rating limitation due to the old conductor that was there is gone, and here's all the changes calculated and the new change in the MVA rating. So this is an example of the line rating. Now let me show you here the history record for this line has a whole lot more entries. It has all the original, there's the original conductor rating when it was entered, the original from terminal rating, the original to terminal rating, and the original overall rating for this line. And what I did is I entered this rating record, but I didn't make the system operating limits in the original entry. So I went back. Now system operating limits, like for example, this line has a thermal rating of 3,000 amps at 40 degrees C, but you cannot load it that high. Something bad will happen if it is outaged. And so I put in a system operating limit of 2,500, and you can see that the operating ratings are different from the planning ratings. And you can also see in my history that I put in these values after the rating record was originally saved. So now I have every field that is changed, its old value and its new value, when it was done, who did it, and what the previous revision of it was. Now you'll probably see a little bit of disconnect here and there in the video. I'm doing it in pieces. So at this point I'm back to the lines find form. Let's go to Washington, Baltimore, number 1, the 161 line, and look at it a little bit more. Let's look at the rating form. Now, one of the things you can do with this, especially using the yellow change notice on the form, you notice that this line is limited at 40, 30, and 20. Well, it's limited at 40 degrees C by a switch and by a trap, but it's also limited at 30 degrees C and 20 degrees C in the continuous rating by a wave trap. So let's pretend to replace these two things with, say, a 2000 amp switch and a 2000 amp wave trap. And you can see now that these are recalculated. Now the line is limited at 40 degrees C by conductor, and the wave trap limit at 30 and 20 degrees C is gone. You can see the changes in the MVA rating, both in the planning ratings and the operating rating. Let me put these back the way they were for another illustration. You see what we've got here is the main from and to terminal information, but it will also have the ability to show the spare. So I've got a spare. By this green shows me that I've got a spare terminal identified on this line, and if I pick it, you'll see that it has different information, different rating limits, different ratings, and you can see that all of the planning and operating ratings for this line would change if the spare is used on this end of the line. If I go back to the main, it goes back to the original. Now you can't save it in this form. I only have these values saved while the main boxes are checked. One other thing that's quite important, let me show you the algorithm constants. I'm going to open up another form, and this one's also fairly busy. But what this is the algorithm constants that are used to calculate all the ratings. These are all equipment constants, the breaker, switch, wave trap, and current transformer constants. These are the defaults, and I'll show you a file with those in it later. These are the present settings for the main and spare of the from end and main, and you can see that the spare on the to end is not set yet. And here's the algorithm form as well as the additional partial CT multiplier. Now what can you do with this? Well, let's assume that 1200 amp wave trap, which is limiting that line, and the switch as well. Let's say you've got a project to replace those in 6 months. Now TVA in its rating methodology allows for exceptions that says that if we're going to fix it in a certain amount of time, we can use the emergency algorithm for the continuous rating. So if I take on the wave trap on the from end, if I take the 180 T max for the emergency and put it in the continuous, and if I change the continuous switch to match, let's put 240 there and 130 there and 240 there. So you now have the continuous rating of the switch on the from end and the continuous rating of the wave trap on the from end based on the same as the emergency rating. Now if I close this, you can see that I now have changed all of these values. I'm also going to show you that the defaults have been modified, and you can see that the ratings have now been increased. You can go back and look at it and see exactly what's different, and there they are. So that's another way that this can be used. The algorithms constants can be used in exceptions in your rating methodology. Now let me show you some of the external files that the program reads when it starts. This is a conductor data file, has all the conductors, a list of conductors, Resistances at 25C. This one's actually a 50C, 75C. Reactance, diameter, and capacitance. Now the 50 degrees C resistance and the reactance value and the capacitance are all the values that go into impedance calculations, which I'm not actually using at the present time, but your 25C, 75C resistance values and your diameter are involved in the rating calculation. Another file that it reads when it starts is the settings file. The settings file, you might call it defaults, gives some starting values for various aspects. One thing that I've had to do, Visual Basic doesn't have a real good formatted numeric text box, so I had to create my own text box, a character-based text box that operated a certain way. So these two things are some values that turn this or that on or off. Then the form colors, there's the background form color, the edit back color, that's the edit cell back color, and the spare edit cell back color, etc. All of these colors. Now, one thing we did with the Visual Fox Pro version of the database at TVA was that when it came time, twice a year actually, in the spring and fall, to make our base cases each year, we would bring the database fully up to speed, fully up to date, and we would freeze it. We would place a copy in another directory on the server, and on that copy we would change the back color to a different color so that you knew whenever you were running that particular database, you see the color as being odd, and you know that you're running a frozen copy of the database, not the currently running ongoing maintenance copy of the database. Here is a minimum and maximum in and out of service date that's acceptable to the program. Here are your area values, and I think I give up to 9 or 10, the capability of up to 9 or 10 of those, and 9 or 10 zones, maybe 20 zones. Owners, these are all the drop downs in the bus data. And then I said, you remember in the bus naming convention, there was a code at the start of every bus name. And here is the default values for that. Here's a 0 for bus voltages between 0.01 and 1.1. Here's your 5, that's 161 kV for voltages between 150 and 200. There's the 500 kV from 450 to 700, or a nominal 500. And then the bottom of the defaults file, or the settings file, are all the rating algorithms. Here's the conductor wind speed, the emissivity and absorptivity. I've got some notes out to the side. Breaker algorithm constants, switch algorithm constants, wave travel algorithm constants, CT algorithm constants, and the partial CT exponent. So these are all the default algorithm constants that you'll find. If you'll recall, when I opened that algorithm form up, on the left-hand side were all the defaults. So before I go any farther, let me go back and mention that the defaults file, or the settings file, the user can edit that and put his own rating algorithm constants, or areas designation, zones, owners. He can change the coloration, background color of the form, the background color of the edit cell and the spare line edit cell, etc. So all of that stuff is changeable. Now, before we started, or at the start of the video, I said I was going to make some changes to the database so that you could see how to do this. In the interest of time, let's only do one of these, and let's do the one that's a little more complicated. Let's break the Baltimore, Washington #1 line, add Annapolis tap, and then put in the Annapolis 161 kV tap line. So before I break that line, or in order to break that line, I have to change the out of service date of the existing line. So I'm going to make the out of service date 5/31/2014, 1 day before the new project takes effect. And when I hit save, I've made a mistake here, because I've tried to change the termination date of the overall line before I change the termination date of the impedance and rating record. So I've got to go back and get that done. So here's my impedance record, 5/31/2014. I'll save that, and I have the ability to let you decide not to save something. You have to save it. You have to say you want to save it twice. I also give you the ability to put in a save comment. So I'm going to save this. Then I'm going to change my rating out of service date to 5/31/2014. And see that the save comment is kept until you change it. Now I can change 5/31/2014. So you can now see that Baltimore Washington #1 line has an out of service date of 5/31/2014. Now before I can add the new lines, I have to add the new buses. And those bus numbers are for the Annapolis TAP 537796. That bus is an available unused bus number. I'll make that a load flow bus. Its in service date is going to be 6/1/2014, and it'll go all the way out to the end of time, so to speak. That's a 161 kV bus. I'm not going to fill in all the information, just to move things along. Another bus is the Annapolis bus itself, 537797. That bus is available. Make it a load flow bus, in service date. That also is a 161 bus. So if we look at our buses, we'll see that we now have the Annapolis TAP and Annapolis bus. So let's add the lines. New line. The first line is Baltimore to the Annapolis TAP, 532701. And you can enter via a little drop down browse window. So if I say ANNA, I can get the Annapolis TAP I could pick from a list. Let's make that circuit 1. The in-service date is 6/1/2014 all the way out. And it's going to check and make sure that the bus in and out of service date ranges will accommodate this line range. I'm not going to fill in everything else. Let's put in the second line. That's the let's go from Washington, 544/621. Oops. $537,796. And this time I'm not sure I've got all the programming exactly right, but you can see that it chose my in-service date from the later of the two buses. So I'm going to save that. And finally we need to do the TAP, 537796 to 537797. Now if I look at the lines, I have Baltimore Annapolis tap, Washington Annapolis tap, and Annapolis tap to Annapolis, all in there from 6/1/2014 to the end of time, and the Baltimore Washington line terminates at 5/31/14. Now one thing I didn't show you earlier, let me go to the Baltimore New York 500 line, which has some good rating data in it. I didn't show you the short-term ratings. There are 3 rating categories provided: continuous, emergency, and short-term. Emergency typically is considered 4 hours, short-term 1 hour, but you can turn on the short-term rating. If you know that all the data is good data, you can turn that on. Now, all the ones that are calculatable will be calculated for you. Any that aren't will be blank, so I would have to add this information and this information if I wanted to keep the short-term rating. Let me save it like it is, and I've still got demonstration. I can change this to something else, save it, and if I go look at it now, the short-term rating will be filled in. Of course, I didn't bother filling in the secondary device limits for the short-term rating. Two more subjects to go, and hopefully I'll be through. I told you at the start of the video that this is a pretty large undertaking, and what I've shown here is sort of an outline of what I would put in the database. And the items in red are the things that I've more or less finished. I've got edit new buses, edit new lines, and add and edit impedance and rating. There's also the load forecast assignment that needs to be done for the buses. There needs to be a place to put the load forecast. Need to do in and out of service flags and sectionalizing information perhaps for lines. Need to add the zero sequence mutual impedances. Need to add transformers, complete, impedance, rating, taps, seasonal in service, sectionalizing, etc. Generator data, impedance, reactive and voltage control, supply forecast, dynamic stability models, the model, the governor, exciter, stabilizer, shunt data, specifically switch shunt data. And then there would be some utilities, user management information, program defaults, and also you probably need a direct editing feature where if the program doesn't enable you to fix one specific little thing, you can go in and fix that one thing. So that's the overall database. Now there needs to be some sort of a diagram or plotting. I've been working the last few days on the possibility of doing that within a form in the program, but at any rate a diagram drafting. And then there's the base case creation, making load flows, fault analysis, and dynamic stability base cases. So, you know, as you can see, it's still a very large undertaking, and I'm not very far into it at all. And actually, as I think I implied at the front, I don't really intend to go a whole lot farther without some impetus. Now let me go, one more discussion needs to be held here. I ran into one of my former co-workers a few weeks ago who told me that NERC has started making a lot of noise about making the planning model the same as the operating or ESS models. So I got these two pictures from a Power World integrated topology processor document. And, you know, they point out that, for example, the full topology would look like this: maybe a ring bus, a single bus in the middle of a line, and then a breaker and a half scheme at the other end. But if you did that in a planning model, all you would have is one bus at the left end, a bus at the middle, and a bus at the right. So it may be that the industry is moving fast enough. Of course, looking at the database that I've presently designed, it is essentially a bus branch model, which is the planning model. It's not a node breaker model, which is the full topology model. I would think that you could modify my database, that I could do some modifications and possibly create a node breaker model. But I think the planning for that kind of thing is not fully fleshed out at this point. So I wonder, if you were starting from scratch, what you might do is build a database similar to what I have built, but you would do the data entry in sort of a hybrid scheme, whereby, for example, you might put a branch in for each leg of a ring bus, and then the branch for the line would not have a breaker at this end, but would have a breaker at this end. Of course, the rating information for this end, there would be terminal information at this end of the line, because you've got relays that trip that line. You've got secondary devices that see currents based on this line flow, in addition to these branch flows. So you could probably do some form of hybrid, perhaps, and still use a database that's tailored for a bus branch model. Finally, let me give you my email addresses. My name again is John Cleland. There's two email addresses. One is, of course, Gmail. The other is from my local power board. I'm connected to their fiber optic network, electric power board. I live in Chattanooga. Also, I'd like to recommend that you check out my overhead transmission line constants program. It is pretty much a fully finished program. I really am proud of it, in that it's a very efficient way to build the transmission line impedance problem, and provide a very detailed output that's very useful. So it's another YouTube video that I've got out there. Please check that out. And I just finally would like to say that I know this has been somewhat of a haphazard approach. I'm not a real polished person, and the demonstration of my program has had some fits and starts, but I hope you found it very interesting, and I appreciate you watching. Thanks a lot. Bye.